So, very good morning, all of you. And thank you, Professor Rao, for my brief introduction. So, today we will discuss about hybrid machining processes. If we check the date when this process has been started, it is really difficult to find out because this manufacturing processes or the machining process or the metal removal process is starting from the very primitive age, and it has been practiced by the ancient peoples for making weapons or tools. For example, this is a making of hand axes during stone ages. So our this the left one photo is for the primitive tools used by the ancient people, and the right one is the basically the this picture shows the evolution of the processes. These are the primitive one, and now the present day scenario that this one this one is the that micro shaft of diameter 15 micron. I think the if you know the diameter of hair, human hair, it is near about it ranges near about 20 micron to 15 micron. That means this shaft is the diameter of this shaft is lower than the diameter of the human hair, and that can be produced by only micro turning. And this structure is made by micro WDM. So now this is the present condition of any machining process, and this is the evolution of machining process from the primitive to present day scenario. So today we'll discuss all about that hybrid machining process, and before that we will discuss the basic of machining processes and how the transformation occur from machining to or traditional machining to the advanced machining process and advanced machining to hybrid machining process. So take a look of my content of the presentation talk. My presentation talk will start with the introduction part, in which we discuss about the basic definition of the machining process, and after that we'll discuss the advanced machining process or the necessity of advanced machining process, why actually it is needed, and then moving on hybrid machining process. We'll discuss about hybrid machining process, its classifications, its types, its typical examples, and then we discuss electrochemical honing in detail. Basically, electrochemical honing is the electrochemical based hybrid machining process, and further we will discuss about the future scope or the scope that can be carried out for future research work. So moving on. So this is my objective of this presentation, to share my knowledge and findings of hybrid machining process, to encourage the research community to carry out research in this field, to mature these processes, to make them commercialized. This hybrid machining since last decade, these hybrid machining processes are emerging in the different industries, and they are going to replace all the advanced and traditional machining processes day by day. But main problem with these processes are that these processes are not it is very much difficult for us to get a proper setup or proper machine equipment for this hybrid machining process. If we wish to carry out any hybrid machining processes, we have to fabricate it in your lab or in your in-house. You have to develop in-house. So it is the main problem with this processes, this group of machining processes. And so my presentation talks is for to give a details understanding or my findings, so that you can carry out your research work in this field, or to make these processes commercialized. So moving on, take a look of the basic definition of the machining process. Machining is basically a subtractive type manufacturing process in which surplus materials is removed in the form of chips to impart desired shape, size, and finishing to the final object, using a suitable cutting tool and using a suitable relative motion between cutting tool and workpiece. This definition is very well known to us, and main highlight of this definition is that subtractive type, surplus material is removed, suitable cutting tool, and suitable relative motion. We all know that manufacturing process basically that is the process or the method of value addition. That means we have to convert the raw material into some finished product by some value addition. That is the definition of manufacturing process. And we all know the manufacturing processes are classified in 4 groups: additive, subtractive, formative, and assembly type. Additive means that final object or the finished product will be obtained by addition of material, for example casting, for example rapid prototyping. Next, subtractive type manufacturing process, in which we remove the extra metal, and we'll get the final product, for example machining operations or machining processes. Then formative type manufacturing process, in which we will get the final product by plastic deformation of material, for example rolling, forging, extrusion, etc. and then assembly type, in which you get the final product by joining of materials, for example adhesive joining, welding, riveting, etc. So coming to the definition of machining process, it is basically a subtractive type manufacturing process, because the as final object will be obtained by the removal of material or a removal of extra material. Main highlight is the suitable cutting tool. If we check the images, that this is we are very much popular, well known about these operations. This operation is turning operation, this is drilling operation, and this is milling operation. If you take the example of turning operation, when this tool comes in contact with this rotating workpiece, it compresses the workpiece and produces severe plastic deformation, and material is removed by shearing action. And this phenomena can only be possible if the tool is harder than the workpiece. Suppose if we wish to turn a steel rod, we have to choose a high-speed steel cutting tool, high-speed steel as cutting tool. But it is really difficult for us to cut a steel rod by using a cutting tool that is made of aluminum. So the basic motto, and the same story is same for the drilling and milling. The basic tagline of machining process is that the tool should be harder than the workpiece. And this set of machining process which follows this tagline, the tool should be harder than the workpiece, are known as traditional machining processes or conventional machining processes. So moving on, there are some photographs which indicates a international event, and it is, I know you all know about it, it is obviously Second World War. And this is the most detrimental after effect of Second World War, that is the explosion of Hiroshima. So besides this nightmare of human civilization, this Second World War compelled us to think in a different way. And this is the sum of the colorful after effect of Second World War. The generation or development of new technological industries like automotive industries, aerospace industries, satellite industries, marine industries, etc. Up to Second World War, the conventional or traditional machining were very much popular. But as these technological industries are developed after Second World War, and the products or the components are used in these industries are basically employed in a very hostile environment. For example, satellite. The component used in the satellite of space is really the environment of the space is completely different from the atmospheric environment, and therefore we need some new or non-traditional materials. So we can say that the development of advanced technological industries like aerospace, automotive, and satellite is accompanied by the development of very hard, high-strength, difficult to machine materials such as stainless steel, superalloys, titaniums, and ceramics. So we need some new techniques, because the traditional machining processes have the tagline that tools should be harder than the workpiece. But now these materials, the hardness of these materials is harder than the material used in traditional tools. So we have to move on, and we have to think in a different way. So if we produce complex geometries and maintaining high dimensional accuracy in such materials, really found really difficult by conventional machining processes. These problems necessitates the exploration of advanced machining processes. These advanced machining processes are characterized by higher power consumption and low MRR, and they are chosen for their special capabilities to produce extremely complex part and machine uncanny materials. Okay. So this is the main boundary conditions of any AMP or advanced machining processes. If we wish to cut, AMPs can be cut for any material or can be used for any material, but it should be used for which materials which are really difficult to cut by traditional processes. Suppose it is really, if we wish to cut or if we wish to turn an aluminum rod, it is really, aluminum is very soft material, and you can easily cut aluminum material by any conventional machining processes like turning. If we wish to cut titanium, then we can go for advanced machining processes. So this is the main criteria or main boundary condition of using the AMPs, that AMPs can be used for only for complex or tricky geometry or difficult materials or difficult to cut materials, because these AMPs are associated with high power consumption, high initial cost, and low MRR. The MRR of AMPs in most of the cases is lesser than the conventional techniques. So normally advanced. So in case of traditional machining processes, the fundamental concept is that tools should be harder than the workpiece. So we have to change this concept, or we have to use some new energy sources or new technique to remove the material. So which type of energy sources is used? On the basis of that, advanced machining processes are classified in four groups: mechanical type, chemical type, electrochemical type, and thermoelectric type. Mechanical type, in which material is removed by erosion of high velocity particles, for example AGM and USM. AGM stand for abrasive jet machining and USM stand for ultrasonic machining. Then comes the chemical group, that in which the material is removed by corrosive action of reagent, for example chemical machining. Then electrochemical type, in which material is removed by ion displacement or anodic dissolutions, for example ECM and ECD. ECM stand for electrochemical machining and ECD stand for electrochemical drilling. And finally thermoelectric type, that in which material is removed by melting and vaporization, for example EDM and EBM. Electric discharge machining and EBM stand for electron beam machining. So this is basically a list of AMPs. Those are very much popular nowadays in industries. On the basically this classification is there, and their mechanism and material removal is there. For example, mechanical, if it is mechanical type, then the mechanism of material removal is erosion. For example, AGM, USM. If it is electrochemical type, the mechanical mechanism of material removal is ion displacement, and electric current will be used as energy sources. Similarly, for chemical, it is corrosive agent, and thermoelectric, it is either electric spark, high-speed electrons, powerful radiation, ionized substance, or ionized substances. This table basically is showing a comparative study of process capability of different AMPs. In case of, if we look the MRR, it is very low, very much lower than the traditional processes. The MRR of PAM is highest, that is 75,000 mm³ per minute, but the surface finish is very rough. Surface finish is not up to the mark. Okay, so if we wish to use any advanced machining process for our application, we have to choose this wisely. So these processes, these advanced machining processes are very much popular up to 1970s or 1980s. But during that time, it was found that these processes are also having some drawbacks. So, for example, I think we are all known about the ECM process, or electrochemical machining process. In electrochemical machining process, an anode is there, that is workpiece. Workpiece is connected to the positive part, and tool is connected to the negative part, and a gap is there in between tool and negative tool and positive workpiece. That gap is basically inter-electrode gap, and that is provided to avoid the direct metal to metal contact or to avoid the short circuit. When this gap is flooded with proper electrolyte, the electric circuit completes, and due to that, ECM process or electrolytic dissolution process starts. But main problem with that, in case of electrolyte, normally aqueous solution of any salt or any basic or acid is used as electrolyte. So if we, during the process, this aqueous solution or the water is also dissolute in H plus and OH minus, and as a result, the oxygen is evolved out at the anodic part or workpiece part. This oxygen reacts with the workpiece, a metallic workpiece, and produces a metallic oxide layer. And this layer is basically a passive. This layer is basically an insulating layer. So this layer further stops the process, or to further acts as a insulating layer on the workpiece and stops the process. So this is the main problem with the ECM process. The ECM, in case of ECM process, the MRR is good because material is removed by the material is removed in atomic scale. So surface finish is good, but MRR is good because rate of dissolution is high. But main problem with that, after few cycles, it stops due to generation of this metal oxide layer or insulating layer. So we have to remove these drawbacks, and to remove these drawbacks, or to remove this, to eradicate these problems of advanced machining processes, hybrid machining processes are conceptualized by combining two or more than two AMPs, two or more than two advanced machining processes, or AMPs or advanced machining processes with conventional machining processes, so that we can add up, or we can sum up the benefits of both the processes, both the constituent processes, and minimizes the drawbacks of different processes. So basically, this hybrid measuring process can be characterized by 1 is plus 1 is equal to 3 equation. If normally 1 plus 1 is equal to 2, but we are adding two processes, so we add already sum up the benefit of both the processes, and plus one thing is there, that is we also eradicate the drawbacks of both the processes. That means 1 plus 1 is equal to 3, not 1 plus 1 is equal to 2. So moving on, this is a typical example of hybrid machining processes, that is electrochemical drilling, in which, or electrochemical grinding, in which we combine electrochemical machining process and mechanical grinding. The electrochemical dissolution phase of electrochemical machining combines with mechanical grinding or mechanical abrsion phase of mechanical grinding, and as a result we will get the final object. So basically, hybrid machining processes, or the constituent, on the basis of constituent process, these hybrid machining processes are classified in two groups. First one is that both the processes, or both the constituent processes, are directly involving material removal. For example, electrochemical grinding. Electrochemical grinding is a combination of electrochemical machining and mechanical grinding. Electrochemical machining and mechanical grinding both removes the material from the workpiece. Second classification, that is one process directly removes the material, while other process only assist by making the machining environment favorable. For example, ultrasonic assisted abrasive flow machining. Abrasive flow machining is basically a mechanical type advanced machining processes in which material is removed by the flow of abrasive slurry. Okay, so we add ultrasonic assistant as a performance multiplier of the process. So in this process, ultrasonic assisted abrasive flow machining, in this hybrid machining process, ultrasonic assistance never participate in material removal, but it actually multiply the performance of abrasive machining. So this is the main classification of hybrid machining processes. First one, where both the processes removes the material from the workpiece, and second one, in which one constituent process removes the material and other acts as performance multiplier. This diagram showing the complete list of hybrid machining processes which are very much popular nowadays in research labs only, not in industries. Okay, the round one are the constituent process, and the elliptical one are the resulting hybrid machining processes. For example, this ECM process, or electrochemical machining process, combines with mechanical honing or the conventional honing and produces electrochemical honing or electrochemical finishing as hybrid machining process. Similarly, lapping combines with ultrasonic machining and produces ultrasonic assisted lapping. This ultrasonic assisted machining combines with AFM and produce ultrasonic assisted AFM, or ultrasonic assisted abrasive flow machining. Here in this case, in ECH and ECF and USL, the one constituent process is advanced machining process, the ECM is advanced machining process, while this honing is conventional machining process. But in case of USAFM, USM is also, ESM and AFM both are advanced machining processes. So similarly, US ECM is there, ECDM is there. ECDM is formed of ECM and EDM. Then ECDG is there. In ECDG, three constituent processes are there. First one is the ECM, second one is EDM, and third one is grinding. This is known as electrochemical discharge grinding. So these hybrid machining processes are developed to minimize or to reduce the drawbacks of, or the problems we experience during advanced machining processes. This is a schematic diagram of the process principle of electrochemical discharge machining. Basically, main problem with the electric discharge machining is that in case of if we wish to carry out electric discharge machining, the main limitation is that the workpiece should be conductive in nature. So it is really a big problem for us, because we cannot use this setup, or you cannot use this machine setup, or we cannot use this fundamental concept for the non-conductive material. So we club electrochemical dissolution with electrodischarge erosion and produces a new technique, that is electrochemical discharge machining, which can be capable, which is capable to machine whether it is conductive or whether it is a non-conductive material. This is abrasive electrodischarge grinding. Here, electrodischarge erosion is combined with mechanical abrasion to improve the performance of electric discharge machining process. Electrochemical discharge grinding. In this process, three constituent processes are there: electrochemical dissolutions, mechanical abrasion, and electrodischarge erosion. Then ultrasonic assisted lapping, where ultrasonic vibrations combines with mechanical abrasion and produce a new or hybrid technique, that is ultrasonic assisted lapping, which characteristics or whose the process capability is far better than the both the constituent process, that is ultrasonic vibration or ultrasonic machining and mechanical abrasion. Then ultrasonic assisted electrochemical machining, that in which ultrasonic vibration combines with electrochemical dissolutions. Then ultrasonic assisted electric discharge machining, that is in which ultrasonic vibration combines with electrodischarge erosion. And laser assisted electrochemical machining, in which laser basically assisted laser assistance is added to the electrochemical dissolution to improve its performance or process capability. So this is the highlight of main so far. Actually, main highlights is that we already talked about main difference between AMPs and the conventional machining. The problem with conventional machining is that this tagline is there: the tool should be hidden on the workpiece. This concept is completely gone in case of AMPs or advanced machining processes. In advanced machining processes, the energy sources used for material removal is completely different from the conventional one, and therefore that tagline is of no use in case of AMPs. I already discussed about the definition and classification of hybrid machining processes. Okay, the necessity of hybrid machining processes: basically hybrid machining processes are required or basically are needed to minimize the drawbacks of AMPs. And we already talked about different hybrid machining processes which are very much popular in the research lab only. So this is the main highlight we already discussed about. So now moving on, we will discuss about the electrochemical honing process in detail. Basically, electrochemical honing, a typical example of hybrid machining processes. It is an electrochemical based hybrid machining process. We did a lot of work on electrochemical honing, and I'm here to share my findings and the knowledge on this field. So starting for the basics part, that is ECH basically combines two processes, ECM and mechanical honing. ECM stands for electrochemical machining, in which material is removed by the anodic dissolutions, and mechanical honing. Mechanical honing is basically a conventional type, subtractive type manufacturing processes. In ECH, ECM provides faster material removal because in case of ECM, material is removed by the anodic dissolutions, so the MRR is higher. Stress-free surface, as in case of ECM, tools never comes into contact with the workpiece, so the workpiece surface is completely stress-free, and good surface finish. In ECM, material is removed by the anodic dissolutions, or material is removed at the atomic scale. As a result, we'll get a good surface finish on the workpiece. That is up to micro or nano level. Okay. The mechanical honing in ECH, mechanical honing provide control generation of functional surface. Distinct cross-hatch layer pattern, because continuous simultaneous rotating and reciprocating motion is there, and as a result, the resulting layer pattern will be of cross-hatch. This layer pattern, or this cross-hatch layer pattern, is having a good typological property because the oil retentivity capacity of this layer pattern is higher. So if any component is going to use in any where typology is really a big issue, typological phenomena is big issue, then we can go for honing process or electrochemical honing process. Then residual stresses induced surface and ability to correct macrogeometrical errors. So start with the first constituent process, that is electrochemical machining. This is based on the Faraday's laws of electrolysis. This is advanced machining processes. Here tool is connected to, I already discussed about the electrochemical machining. Here tool is connected to the negative part of the power supply and workpiece is connected to the positive part of the power supply. And a gap is there in between tool and workpiece to prevent the direct metal to metal contact or to prevent the short circuit. And this gap is known as IEG or inter-electrode gap. When a proper electrolyte is there or proper electrolyte is flooded in this gap, this electric circuit completes and anodic dissolution starts. This is the fundamental concept, or this is the process principle of electrochemical machining process. So these are typical reactions. Some of the reactions are there. If we use iron, if we use iron as workpiece, copper as tool, and NaCl aqueous solution as electrolyte. And this is the final outcome, the precipitation of ferric hydroxide and evolution of hydrogen gas. These are typical examples, typical advantages of an application of electrochemical machining processes. That in ECM, electrolyte removes dissolution products, metal hydroxide, heat, gas bubbles generated in inter-electrode gap. As continuous flushing is there, continuous flushing of electrolyte is there, and therefore it can free the machining zone from this type of from metal debris or any gas bubbles or heat. ECM can process complex cavities in high strength materials and produce biofree surface. In case of ECM, the material is removed by anodic dissolution, so material hardness is not a limitation. So you can process any material, whether it is very hard or not. But the limitation is that material should be conductive in nature. No, in ECM, no direct contact between tool and workpiece, which results in no tool wear. Material is removed in atomic scale, obviously produces good surface finish. Various industrial techniques have been developed on this basis of ECM concept. For example, electrochemical drilling, electrolytic drilling, safe to electrolytic machining, etc. These are typical examples of electrochemical machining, electrochemical process-based machining processes. First one is the electrochemical drilling. Second one is electrochemical jet drilling, where a conductive jet is used. Jet is used to drill the workpiece, and this process can be used for superalloys also. And it produces a hole of aspect ratio near about 50 to 80. This is electrochemical hole reburing, and these are defined typical. Basically, the components can be finished by electrochemical machining process. Now moving to the next constituent, that is honing. Honing is a subtractive type manufacturing process in which materials are removed in the cutting action of bonded abrasive skeins. It is used to improve the form, dimensional precision, surface quality of workpiece under constant surface contact with the tool. Honing is applied after precision machining. Honing is basically the MRR of honing, or the basically material removal capability of honing is very low, and it can be used after grinding process for only to improve the finishing or the macro geometrical errors. Normally, three types of honings are very much popular in industries. First one, that is longitudinal stroke honing, or frequently are referred to as honing, short stroke honing, or designated fine honing, and super finishing or gear honing. So longitudinal stroke honing used for connecting rod holes, brake drum, and cylinder liners. Short stroke honing used for crankshaft or rotor shaft. And gear honing are used for provide a precision finishing to the gears. So coming to the our basically combination of both these processes, that is the hybrid machining process, that is electrochemical honing, which combines both these processes, and as a result we'll get 5 to 10 times faster than conventional honing, this MRR, and 4 times faster than grinding, and the surface finish up to 0.05 micrometer can be achieved by this process. Electrochemical honing is started in the 1963, but it is accelerated in the year of 1981 But the main problem with this process is the development of the design of the tooling system. This process is generally used for finishing either internal cylindrical surface, and that is known as or termed as ECH of cylinders, or gears, and that is termed of ECH of gears. Coming to the process principle of this process, in step 1, uh, in the step in ECH process, ECM process and honing process combines. The electrochemical dissolution phase combines with electrochemical machining phase, and mechanical abrasion of honing phase combines with it and produce the and will get the final output. In step 1, cathode is there, workpiece is there, and a large amount of asperities and peaks and valleys are there, and a proper electrolyte is flooded in between cathode and the workpiece, or in the gap between cathode and workpiece. Now, as the electrolyte or anodic dissolution starts, the metal is removed from the by ion displacement. Metal is removed from the workpiece, and the asperities will be lowered down. But due to the formation of metallic oxide, or formation of, as aqua solution is there, and water will be dissolved in hydrogen and oxygen, and this oxygen will react with the workpiece, there is a chances of formation of metallic oxide layer, and this layer is basically a insulating in nature, and this layer this layer will cover the workpiece surface and make the workpiece non-conductive. So as a result, the ECM process will stop. Now honing or abrasion action comes into picture, which scraps the metal oxide, this insulating layer, from the high spot and produces fresh metal for further electrochemical dissolutions, and thus these honing actions accelerates the process. So basically in this process, we already told that AMPs are having some drawbacks, and we combine some other process with AMPs to produce hybrid measuring process, so that we can add up the benefits of both the process, and we can remove the or eradicate the drawbacks of constituent processes. So here ECM is having some benefits, for example good surface finish, high MRR, but the problem is that formation of insulating layer, and we have to remove that drawback, and that's why we add honing action or scrubbing action with it, and thus we remove the problem, and we get a better process, that is electrochemical honing, whose capability is many times better than the electrochemical machining process or mechanical honing process. This is typical ECH or electrochemical honing tool that is used for ECH of cylinders. So coming to the next part, that is ECH of gears. We are very much well known that gears are vital element of any mechanical industries to transmit power and motion efficiently and economically. The transverse rate is almost 99%. And annually 2-3 billion gears are consumed worldwide, with turnover running into several billion euros. So gear teeth surface should be smooth and error-free, so smooth and noiseless power motion transmission. If there is any discontinuities in gear teeth profile, we should encourage the chances of fatigue failure and reduce the service life or the lifespan. So gear finishing is the only criteria, or the gear finishing is the only remedy for this. So we applied or employed this technique, ECH process, to improve or to provide a finishing to the gears. Conventional gear, there are so many conventional gear finishing techniques like gear grinding, gear saving, gear honing, and gear lapping, but those are costly, time consuming, and having material hardness limitation, because in conventional techniques the tool should be harder than the workpiece material, and therefore there is a limitation of the material hardness. If this material, the workpiece material, is harder than the grinding wheel or the abrasive used for gear honing or gear lapping, then it is difficult to remove the material, or it is difficult to finish the workpiece. Therefore these processes are really having material hardness limitation. Moreover, it is costly and time consuming, so need some different solution, and for that ECH of gears is there. It is initiated by Capello Bartoglio in 1979. Though the ECH process started in the year of 1963, but ECH of gears has been started in the year of 1979, and after that is accelerated by Chen et al. In 1981. The fundamental concept of both the process, whether it is ECH of cylinder, whether it is of ECH of gears, is the same. Fundamental concept of the basic process principle is the same, but main difference is that tooling. The ECH of the tooling of the ECH of gear is completely different from the ECH of cylinders. This is the schematic diagram that's showing the process principle of ECH of gears. In this picture, three gears are there. The middle one, that is workpiece gear, the left one, that is cathode gear, and right one, that is honing gear. Now this workpiece gear acts as driver, and honing gear and cathode gear acts as driven gear in this gear train. Now this workpiece gear is simultaneously rotating and reciprocating. Now just take a look of this cathode gear. This is the broad view or broader view of this cathode gear. This cathode gear is fabricated by sandwiching a conducting gear between two insulating gear and undercutting the profile of conducting gear, then insulating gear. This undercutting will act as the inter-electrode gap or the necessary gap which will prevent the short circuit. Now this workpiece gear and cathode gear and this gap, if this gap is flooded with proper electrolyte, the electrolyte circuit completes and ECM action starts. But after few cycles, after few runs, there is a formation of metal oxide microfilm on the workpiece. That oxide layer is insulating in nature, which will be removed by this scrubbing action of honing gear, and this honing gear will produce some trace metal for further electrochemical dissolutions, and thus will get a better output. So coming to the process parameters of ECH gears, basically process parameters of ECH gears are classified in four groups: power supply related, electric supply related, honing related, and workpiece related. Power supply related parameters are, for example, current is there, pulse of time is there, pulse on time is there, duty cycle, and voltage. Electric supply related parameters are composition, concentration, pressure, temperature, flow chart, flow rate, conductivity, and pH. And type of abrasive particle size, rotating and reciprocating speed, or the ratio of rotating and reciprocating speed are used as honing parameters. Then electrolyte and mechanical properties of workpiece, size of workpiece, and pH comes under this group, this workpiece related parameter. And normally surface integrity aspect of the gears, macro geometry, gear teeth profile, teeth thickness, micro geometrical properties, for example roughness, process capability, MRR can be used as measures of process performance. Beside this, the typological phenomena or the typological property of gear teeth surface can be used as process performance parameter. So coming to the fabrication part of the experimental setup, that basically this is the schematic diagram of the experimental setup of ECH of gears can be used for spur gear. This experimental setup basically consists of four sub elements. First one is the power supply systems, that consist of this power supply system. This consists of this power supply system and the wires, and then electrolyte supply system that consists of electrolyte chamber, electrolyte supplying unit, heat exchanger, etc. And then tooling systems that consist of this workpiece gear, cathode gear, and this rack and pinion system. And finally, the last one, that is fixtures or machining frame. This is the schematic diagram of experimental setup that is used for bevel gear. Here, two bevel gears are used, first one and second one. Here, this bevel gear is used as workpiece, and these both are used as tooling purpose. Here, that a gap is there. This tooling are basically fabricated by clubbing two different gears. One is made of any conducting material. For my case, it is copper, and other is made of steel. And after that, the steel is coated with any non-conductive abrasive particles. So basically, we club cathode and honing in a single tool. Okay. And this is the photographic view of the experimental setup that has been developed in the that has been developed in the developed in our lab. Okay. This is power supply unit. This is pump and electro supply unit. This settling tank, reservoir is there, heat exchanger is there, because so that we can maintain the temperature of electrolyte, because basically the conductivity of electrolyte is very much responsible for the processes, this electrolyte or iron anodic dissolution process. And by using this heat exchanger we can control the temperature, and thus we can control the conductivity of the electrolyte. So heat exchanger is there, flow meter and pressure gauges are there, and this is the basically tool and tooling arrangement, that's motion supply to the tooling. And this is the machining chamber where actual operation will be carried out. Okay, and this machining chamber consists of normally three types of gears: workpiece gear, one cathode gear, and one honing gear. So the broader view of this machining chamber is here. This is workpiece gear. It is made of steel, and this is the combined, or this is the fabricated tooling, that the middle one, that is shown in red or brown color, that is made of copper, and it will be act as cathode gear. And the upper and lower, that white one are made of basically steel, and for after that it is coated with non-conductive abrasives. Non-conductive abrasives. So this workpiece gear acts as driver, and this abrasive coated gear will be act as driven. Okay, there's a gap in between. This profile of the copper gear is the diameter of the copper gear is a bit lower than the diameter of the this abrasive coated gear. As a result, during the motion or during the process, this copper gear never comes into contact with the workpiece gear. Okay, now if we provide a proper electrolyte supply in between this gap, the electrolyte circuit completes and the process starts. There is a rack and period arrangement is there, so that we can move that block in left side or right side, so that we can accommodate different sizes of gears. Whether if we for application, if we require some gear of larger diameter, then we have to move this block. So basically this part is made to make it more commercialized. Rest of the part of the fixtures and the machining chambers are made of either any non-conductive material. For example, this work table is made of bakelite. This work chamber is made of perpex, so that we can minimizes the chances of getting current shock. This is the machining chamber that has been developed for electrochemical honing of helical gears. Here, this workpiece gear is helical one. This part is used as honing gear, and this is the cathode tool. Here, copper gear, that is conductive gear, is sandwiched between two bakelite gear, and undercutting the profile of copper gear, then bakelite gear. So when during the motion, this workpiece gear will provide the motion to the bakelite gear, not the copper gear. So a gap is in between there, that will be act as inter-electrode gap. And this is the broader view of the developed cathode gear. A bush is there, that is made of brass, to provide the necessary current supply to the shaft and to this copper gear. This is the machining chamber developed for the electrochemical honing for bevel gears. Here two blocks are there, and a slot is there on this slideway, so that we can easily move these blocks and accommodate different sizes of gear if it is required. Now coming to the experimental outcome. This is basically a comparative study of both the processes, or three processes basically. This is the unfinished profile. This is the bevel gear that is made of simple milling cutter or conventional milling cutter, and as a result, that feed marks are there, bars are there, and surface finish or the surface profile is not so good. Okay, now we use this bevel gear as a workpiece material for the ECH process. And after the process, we'll get two different surfaces. The first one, that is glass surface, that is finished by electrochemical mechanical finishing or electrochemical honing, and the rest part, the second pass, that is only by abrasion. This is the setup, fabrication setup. That means here cathode, this copper is used as cathode, and only front part of this bevel gear will be finished by electrochemical honing process, and the rest of the part of the second part will be finished by this honing part or honing gear, that means by abrasion. So it is carried, this thing is tried because we have to compare the process capability of all the processes for milling, for electrochemical honing and abrasive or honing. So their comparative study is there. This glaze part is for electrochemical finishing, this part is for abrasion, and this is the condition of milling. So you can, from this figure, it is very much clear that electrochemical honing is a better process to provide precision finishing to the gears. So this is the scan version of gears. This is before the process, and this is after the process. Before the process, the surface is not so good and irregularities are there, and that can be removed or that can be eradicated by the ECH process or electrochemical honing process. Now coming to the surface roughness, this after the process, the surface roughness of the workpiece profile or the workpiece has been carried out by non-conductive surface profiler, and we get, that is the 6.8 micron is the before the workpiece, 6.8 micron is the RA value before the processing, and after processing it is 359 nanometer. That means almost 94% improvement in the surface roughness by ECH process that can be obtained. So we can say that this ECH process is obviously a better process for finishing to the to provide finishing to the gears. These are the same micrographs carried out at 500 magnification and 1000 magnification. These micrographs are before machining, before the processing, basically electrochemical honing process. And these micrographs, it is clear from these micrographs that feed marks are there, micro pits are there, cracks are there, and surface finish or surface quality is not so good. And these micrographs are after the workpiece after the process, and it is clear from these micrographs that the surface quality or surface integrity aspects or surface topographical aspects can be improved by the process, because these surfaces are having less number of these feed marks, less amount of micro cracks or pits. So coming to the advantages of ECH process, this process increases the material removal rate, particularly on hard materials and bar-free action, because we combine ECM process with honing process. So we club the MRR of both the processes, first of things. And here most of the material, almost 80 to 90% of the material is removed by the electrochemical machining process or anodic dissolutions. So hardness is not a limiting factor, because the only limitation is that material should be conductive in nature. It improves the accuracy and threefold increase in abrasive efficiency. In this case, tool never comes in contact with the workpiece, and so no tool wear occurs. So no spark is produced and the temperature generated is low, which does not cause metallurgical changes in the workpiece material. A continuous flushing is there, continuous flushing of electrolyte is there, which removes the generated heat from the workpiece zone. As a result, the working temperature is near about 30 to 40 degrees centigrade, and as a result, there will be no metallurgical changes in the workpiece can be experienced. Less space are required between work surface and abrasive stones, because this abrasive particle in this process in ECH, in case of honing, abrasives are used to remove the metal, but in this process, ECH process, honing stones or abrasives are used to just scrap the metal oxide microfilm. so not for material removal. So less pressure is enough to we can so that, to carry out the process. And this process is obviously faster and higher material removal rate with reduced horn wear, and it is about 10 times of that for conventional horning and 4 times for that conventional grinding. But obviously this process has some limitations. First one is that the main limitation is that the workpiece should be conductive in nature. First thing. Second is that huge amount of energy is consumed because a huge there are lots of power supply unit is there, motion supply unit is there, and therefore power consumption is really a big issue for this technique. ECH is more costly than a conventional type because of electrical fluid handling elements and the need for corrosion protection. In this process, normally salt solution, aqua solution of salt, basic or acid is used as electrolyte, and therefore corrosion is really a major headache. And so here and therefore maintenance, proper maintenance is required so that we can eradicate this problem. Blind holes are not easily handled as through holes. In this process, ECH through holes can be easily finished by this process. For blind holes, it is observed that it is not so capable enough, not so capable. So we can say that this is the limitation of ECH process, that it cannot be properly or successfully used for blind holes. Now coming to the application. In ECH, most of the material is removed by ECM action process, keeps the workpiece cool, free and heat distortion, produces bar free and stage free surfaces. This technique can be used for any material, regardless its hardness. Only things that materials should be conductive in nature. Presently, most of the automotive industries are trying to use this technique for finishing internal cylinders, and defense institutions or defense research labs are trying to employ this or starting employing this technique, as it will provide better finishing to the internal cylindrical surface, for example, gun barrels. So this process has been started in the year of 1963. That time only this process has been employed for providing precision fillings to the internal cylinders. In 1979, the ECH of gears has been started, but till date this process is having huge scope of research or is in infancy, basically infancy stage. So we have to there is if we wish to choose this technique or this process as our research career, it is really wise decision. Obviously this will be a wise decision, obviously. So main future scope is that the mechanism of material removal or the ratio of material removed by the electrochemical action and honing action is yet to be discovered or yet to be explained. So main problem is that real-time modeling of the process or the modeling of the process by finite element modeling or FDM is really a need proper attentions. Or we have tried this technique for the material of tried this technique in where workpiece material is steel, but it can be tried for other material, for example titanium, tungsten or other aluminum material. So lots of scope is there for so that lots of scope is there so that we can carry out this process as our future research work. So the key message of this presentation is that electrochemical honing is a electrochemical based hybrid machining process. It is capable to provide micro nano level finishing to the cylindrical surface or gears, and it requires comprehensive study for commercialization in industry. So main problem with this technique is that the setup or the machine setup or the experimental setup is not available in the industries or any research lab. So if you wish to carry out research in this field, we have to fabricate this part. Okay. Or if we order this machine setup for any industry to produce, then it will be cost near about 50 lakh or 60 lakh. But if we wish to fabricate in-house or in-housely, then we can develop it in within 1 or 2 lakh. So it is my suggestion to you, if you wish to carry out this part as your research work, it is better to fabricate this thing, fabricate this setup, and then carry out the defined experimental work. So this is all about the hybrid machining processes and all about the electrochemical honing processes. Some references are there. So queries are always welcome. Any doubt, queries are there. My mail ID is there. You can contact me through this mail ID if you require. And before that, presently we are working in this technique that we are trying to club a ultrasonic assistance to the this process so that we can improve or we can multiply the process performance. This is the schematic diagram of ultrasonic assisted electrochemical honing process. This is rest of the part is same, only this assisted ultrasonic assistance is there. And before closing this presentation, I wish to show some of videos. This is workpiece gear and this is tooling. And this is backlight block is there. This rack and pinion is used to move this block. Okay. Motion is supplied to the workpiece. This workpiece is used working as driver, and this tool is here tool is driven. Before that, only rotational motion was there. Now, simultaneous rotational motion and reciprocal motion is there. So this is in dry condition, and this in this is in wet condition when electrolyte supply is also there. This workpiece is simultaneously rotating and reciprocating, and the proper electrolyte supply is there in between gap in the gap or in the electrode gap. The microprocessor controller unit is there to provide the reciprocating motion by using a stepper motor. This is the power supply unit. This is the inlet of electrical supply. This is for helical gear at wet condition. This helical gear is used as workpiece material, which is rotating and reciprocating simultaneously, and electrolyte supply is there in the electric gap. This is honing tool that is basically opposite coated gear, and this is cathode gear, which is fabricated by clubbing and sandwiching a copper gear between two backlight gear and undercutting the profile of copper gear, then backlight gear. This is the working of PCH of bevel gas in dry condition. No electrical supply is there. It is not so clear actually due to electrolyte supply, but it is PCH of bevel gear with electrolyte supply. So this is all about the electrochemical honing process.